Good day, I'm Maile Matsiba. Welcome back to our channel. Today we continue with our class test 3 of our CIR 123, which is the second chemical engineering module at the University of Pretoria. We're looking at part 3 of class test 3, and this is the 2011 version of class test 3. So we did part 1 and part 2, which was A and B of the question. Now we're looking at C, which says calculate the methanol conversion in the process. So part 3 says calculate the which is C part, it says calculate the methanol conversion in the process. Now, if we're going to calculate the methanol conversion in the process, it's important that we understand that there's a difference between the methanol conversion in the process and the methanol conversion in the reactor. Earlier, we're looking at the methanol conversion in the reactor, and it's important to understand that the methanol conversion in the reactor depends on the stream A, which comes into the reactor, and also stream B, which leaves the reactor. So in that case, we looked at the methanol that is entering the reactor through stream A, and then we're looking also at we analyzed stream B, which was the stream that was leaving the reactor, and we check the methanol in there, and the difference between the two methanols, it helps us to calculate the conversion of methanol in the reactor. However, now they want the conversion of methanol in the process. The concept or the principle is still the same. It's just that this now, instead of focusing on the reactor, we are focusing on the whole process. And in that case, we're going to be looking at stream F, which is the stream that is taking in methanol in the process, and alongside with CH14. So that is stream F. And also look at stream P, which is the stream that is taking methanol out of the process. So methanol is entering through stream F, and as a 98% CH3OH solution, and it's leaving as stream P. So, and we did calculate the properties of stream P, which has the percentages of both CH3OH and C6H14 in the previous parts. So that is actually something that I wanted to explain as we're moving further in this question. So before we go further, I want to write down the equation for the conversion of CHO3 in this process. So let me just write it down and say CH3OH conversion CH3OH conversion is equals to CH3OH that is entering the process, right, minus CH3 that is leaving the process, all over CH3OH that is entering the process, right? And everything else multiplied by 100%. I hope it's easy to see that the 100% is actually at the other side, because I just didn't have a space to put it there. It's actually the 100% multiplies the whole thing. So that is actually the equation for calculating the conversion. And now it takes us to our first step. I actually made up 3 short steps. So in step 1, we're going to calculate the CH3OH entering the process. So we're going to calculate the methanol that is actually entering the process. Calculate the methanol entering the process. Calculate the methanol entering the process, right? So at this point, so our first step, we're going to be calculating the methanol that is entering the process. So, and we know the methanol that is entering the process is actually entering through stream F. And for us to calculate that, we can actually find out how much is stream F and multiply it, because we have the percentage of CHO3, multiply stream F, the moles of stream F, multiplied by the mole fraction of CH3OH, and we'll get the amount of CH3OH in stream F, and that becomes our CH3OH that is entering the process. And doing that, we can simply say CH3OH entering the process, CH3OH entering the process is equals to stream F multiplied by 0.98, 0.98 being the mole fraction of methanol. And then now, what is our stream F? Earlier in the first part, we did calculation on stream F, and we were able to find stream F to be 23.92 kilomole per hour. So we can just substitute that. We don't really need to do recalculation again. So it's 23.92 multiplied by 0.98, and if you use your calculator, that's going to give you 23. That is going to give you 23.4416 kilomole per hour. So now with that said, we know that the amount, this is actually the methanol that is entering the system through stream F. So that actually concludes our step 1. Then we go to our step 2. So in step 2, we're going to calculate the methanol that is leaving the process. So calculate the methanol leaving the process. Right, so we're going to be calculating the methanol that is leaving the process, and like we did here, let me just bring, so now this is actually the methanol that is leaving the process is living in stream P, and we can all remember in the first part that indeed there's actually no methanol, it's only CO and H2. We've discussed that. So the only methanol that is living is in stream P, and stream P we did calculate it in the previous steps, and we find stream P to be 2.58 kilomole per hour. So which means we can just say CH3OH that is leaving the process is equals to P, right, multiplied by, we're going to need P, and we're going to multiply it by the mole fraction of, we're going to multiply it by the mole fraction of CH3OH in here, and we did calculate that in the previous questions, and we found that the percentage of CH3OH in P is actually 18.56%. Sorry, it's actually 81.44%. So if we know the percentage of CH3OH in stream P, and we know P also, we can easily calculate how much of CH3OH is in there. So that's what we'll be doing. We can just say P multiplied by 0.8144, and we know that P is 2.58 kilomole per hour multiplied by 0.1844, and if you use your calculator, it's going to give you 2.101 kilomole per hour. So now, with that said, in this case now we know how much of methanol rather is entering the system, and we know how much methanol is leaving the system. And with that said, we can go back to our equation and calculate the conversion of methanol. And with that said, we can just say, therefore, CH3OH, the conversion, brackets, is equals to CH3OH entering the system. We calculated to be 23.4416 kilomole per hour, right? So we know that it's, the CH3O entering the system is 23.44 kilomole per hour, and minus CH3OH leaving the process is equals to 2. This we calculated here is 2.101 kilomole per hour, all over CH3OH entering the process is 23.4416 kilomole per hour, and if you multiply all that by 100%, then okay, yeah, let me say 100%. I hope it's visible that it's actually 100%. So if you use a calculator, there is gonna give you 91.04%. So that's basically what is it. Let me just write the more pretty 100% here. Yeah. So this actually concludes our part 3 of our CIR 123 and of our cluster 3 of 2011. So thank you for your time, and I hope to meet you again in our next video.